let's go through Lico 354 Russian dough envelopes. And we are going giving a 2D array integer envelopes. And for each envelope, it has two elements, width and height. And it says that one envelope can be put into another when the smaller envelope, the width and height are, I would say, there is strict increasing. The smaller can put into the larger one. So return the maximum number of the envelope you can put number for the Russian dough. Take an example. This example is good because you see for this 5 and 4 and 6, 4. This 6 is greater than 5, but 4 is not, right? So we cannot put this one into this because this one equals. So it will have both width and height increasing. So what we're thinking about is that we can sort one dimension and try to see the other dimension with the longest increasing subsequences. So for example, if we sort the first dimension, right? Then it will be, let's sort by the second, right? If we sort the second dimension, it will be 2, 3, 5, 4, 6, 4, 6, 7, right? If we both sort in ascending order, then we'll see in this case, the longest increasing subsequence is 2, 5, 6, 7, but the result returned is just 3 instead of 4, right? The reason is that this envelope cannot be placed in this kind of envelope. So what we think about is that after we sort, for example, sort this kind of dimension first, for the first element, instead we using the increasing sorting order. For first element, we use a decreasing sorted order. So that is we are using 6, 5. So in this case, if the second dimension, the data have the same, right? We are only pick one element, the largest one. Not necessarily not largest one. We are trying to find the longest increasing, right? So we are pick 2, 5, 6, right? So after this order, we sort for one dimension in increasing and another in decreasing. In this case, if the second dimension, the value are the same, we are always just picking one. Then we look in the LRS for the first dimension, find the longest subsequences. So in this case, we may pick 2, 5, 6. So if we know the sorting first by one dimension in increasing and another dimension in decreasing, in decreasing, we know this mechanism. This question will be converted to LRS problem in the first dimension. So let's write code for this. We are going to sort these envelopes, arrays, sort envelopes. We are going to have A, B. So let's start in the index 1 first, in first dimension, right? So I say if just A1 equals B1, right? With this equals, then we'll sort the first dimension in decreasing order is B0 and B0. Otherwise, we're going to sort the second. That is, we first sort the second dimension in increasing order. A1, B1, right? After we do this sorting, we try to see the first element of the envelope, trying to find its longest increasing subsequences. Of course, we needed to have some corner cases, right? For the envelope length equal to 0, right? Or envelope equals none, or just return 0. So now what we need is that we do the LRS, right? LRS for its first dimension. So the thing is that we for LRS, of course, we can use a for loop, right? And for I, use a DP, right? Longest DPI means the longest increasing subsequence end with this index, right? And for this every I, we use a for loop J smaller than I, and J iterate to 0, right? And if trying to see if nums J is smaller than I, then we can append. Then for every J, we have max, local max. So we'll have a long DPI for after we iterate those kind of J, and have global longest for every DPI, right? So that will be ON squared time complexity. But as we talked in another question, as long as increasing subsequences, we can use some greedy way, right? We have a list, and for this list, if it's empty, we add the number, right? And we try to find for every number we coming arrive, we're trying to find the first element greater equal to this number, right? For example, this number is greater equal to this number, then we replace this number with the arrival number, right? So in this case, we are always trying to keeping more spaces for the incoming number, and we're trying to find the longest in the end what's the length in the list. So doing like a binary search to find the index, and in the end the length will be the LRS, right? So let's still using the second way, the binary search and greedy way to write LRS. So as we talk about, we need to have a list of integer. We call list plus new array list. So now the envelope has been sorted for the second dimension increasing order, first dimension in decreasing order, and we are trying to find the LRS in the first dimension, right? So for every envelope, in envelopes, we'll have each index, both binary search list, envelope, there. So let's say if index equals -1, right? We didn't find, then we just append, right? So we'll have this add. And we p then else we just have this set this index. And we yeah, right. And then in the end, we just return this list of sets. And we'll write the binary search. and we'll have list integer list and int min, right? So we are going to find the first index greater or equal to none, and if this list vector is empty, we just return -1. That means we didn't find root. So in this case, we can append, right? So enter start equals to 0 and equals list dot size -1, right? So we'll say allow this start plus 1, some other end intermediate equals to start plus and minus start divided by 2. So I'll say if we are trying to find the first index greater or equal to, right? So we'll say if this get this mid equals to none, we should still find from the left part. So we'll have end equals to min. And if this is greater equal to, right, then we can write this is smaller than start equals min, else end equals to min, right? And let's say we are trying to find the first. So if we check start satisfy the condition, we list with start greater equal to none, return start, and if end and greater equal to this number, we'll return end. If we didn't find, right, so that no data in the list is greater equal than in the none, then we just return -1. In this case, we are also append to the list. Okay, doing like this way, it is because we have a sorting this n log n, right? And this for every element that there are n elements, that every element that is a binary search. So this will be n log n time complexity. We use a list as a linear, so it will be O in space complexity.